All right, good morning and welcome to our, I believe it's the fourth lecture on Introduction to Finite Element Methods. I can see quite a number of you have joined. It's quite a chilly morning, but I hope we'll be able to move on well. Last week we looked at bar elements. It was kind of a basic or a simple illustration of how we can be able to formulate finite element equation for a 1D element, and we started with the bar element and you see we are developing concept. We are building. So ideally we should start, or we are starting with the very simplified cases. That's why we started with the spring, and I said that spring element is just an illustrative tool. But you're going to find that it will be very useful illustrative tool as you continue with your more knowledge in finite element methods, especially when you are modeling sinking supports. But we said in real life, of course, we do not have cases whereby we're talking of a structural member being a spring, but it can behave like one based on the reaction to or the response to applied loads. So we are moving from simplified case, and then we get to a point where we are starting now to get to real cases. And in this case, if you look at why we are talking of 2D space, consider generally this bar element, which we are calling also a truss element, and I illustrated why we refer to as a truss element, because it's kind of a member or an element that is extracted from a truss structure. So that tells you that if you look at the truss, a typical truss, you expect something like that. Let's take a very simple case of a truss. Maybe it's not very structurally sound. It might collapse, but I want to have as minimum members as possible. And with that, so if you can say this is just a 3-member truss, so this being, let's call this member 1. Okay, this is the first node, the second node, the third node, and then this is, we call this member 1, this member 2, or element 3. So you can see this is a realistic or a real case that we might consider when we are talking of a truss structure. So basically a truss element extracted. So you find like these bars will be oriented, not just like the case we are just considering one direction, but in this case they'll be oriented in different directions. So if you take, basically you've been talking of a truss, you talk of that as the axis, so capital Y, and this is capital X. So this is what we refer to as the global coordinate system, because this is the coordinate system of the structure itself, the overall. But if we are to take an element one by one, like element 1 here, you look at it and you realize the orientation. You see, this is node 1, this is node 2. We said we come from lower node to higher node. So typically what we are saying is that this is the X direction, the direction of the stress for that member 1, and this is the Y direction. So for each of these, like when we come from 2, 3, element 2, 2, 3, so the direction of X, or the horizontal for this member, is that direction. So this is the X for 2, small x, and then this direction now will be the small y for member 2. So you can see these different elements, that constitute a truss structure, they are oriented in different coordinate systems. And that's why today we are purposely looking at this particular case scenario, where we are talking of bar element, yes, but it's oriented in 2D space. And because now from this, you can even now move to space structures, space trusses, right? Like grid. So we're moving from 1D to this space, then you can extend. But for our case of understanding, let's just concentrate to this space. So we are ignoring the Z direction. And now, before I forget, our conclusion of last lecture, when we are just talking of the 1D bar element, what you should notice that if we just take an element by itself like that, okay, that's the element we are considering. And maybe I should let me just make this big screen so that we might be able to see it clearly. So what we are saying is that for this case, This is typically what, basically what we are talking of, a 1D bar element. In each of the nodes, because the D, when you talk of 1D, degree of freedom, 1 degree of freedom per node is like, degree of freedom is number of ways that we can be able to describe either the coordinate of a point or the number of ways that it can be deformed. So we are saying from our initial, what do you call it, assumptions is that this being a truss element, it can only carry axial load, and basically it means it can only stretch or compress. Okay, so what we are talking of is that for each element, individual element, okay, if I take this, it's only that we only need one coordinate, the horizontal, to describe its motion, right? And per node, the degree of freedom is 1. Only horizontal displacement. It can either be to elongate or to compress. U can either be negative or positive, but either way, we just need one coordinate to describe that, the motion or the deformation at one point. Okay. What I was saying before I forget is that we talked of when the load is applied at the nodes, but you may have cases, it's a bar element, but the load is uniformly distributed, like there is friction. Remember, the load is only applied axially. So don't ask why I'm not applying, I'm showing generally the way we show, like a UDL. It's because for a bar element, we are saying the load is applied axially. But now we are saying it's applied, it's UDL. How can this be? Let's say we have a member like this, fixed on a wall. It's kind of a wall bracket. Let's assume it's something to hang. You want to hang. This is the member we want to analyze. For to talk of a TIBA section, then here maybe we attach another member or something, and then we want to hang something like a weighing machine or weighing scale here. Okay, we want to have a weighing scale here. So you can see this is different than when it could have just been fixed at this end, because it seems if we are using bolting, if this is bolted like that or nailed, the load is distributed uniformly, although the load is acting downward, right? But if we are analyzing this member which is fixed on this wall, if this is our interest, then it means the load is distributed uniformly along the length of the member, but axially. So when you have cases like this, and this is node 1, let's talk of node I here, and node J here. So this UDL, because we said the load is applied at the node, have to be resolved the node. So how do we do this? So if this is node I and J, and then let's assume this is uniformly distributed load Q, or you can call it W. Yeah. So this could be maybe a kilonewton per meter length, per unit length. So you need to resolve this. Half of it comes here. So if this length is, the total length is L, then it means we resolve our member of our element like that. This is node I, node J. So in this node, we say the load applied is Q, L over 2. And applied here is Q, L over 2. Okay. When we have a UDL. If we had multiple nodes, let's say like we have node I, then or let's call it node 1, then we had another node 2 here, then we had another node 3 here, okay, something like that. Then in a similar case, you just need to resolve the node, the load at the nodes. So half of this comes to this node, half of this comes to this node, and half of this comes to this node. So basically at node 2, if the total length is if now, let me just say, because of this now new node, let's say up to this point, this is L of L, and then this is L, or this is L over 2, and then this is L over 2, okay? Then it means the load that we come to this node is all this region. So it's Q times L over 2. And then this is a quarter of L, of L, because now L over 2 you have divided by 2. So Q times L over 4 will come to this node. Okay, so I hope it should be clear and simple so far. But that's just a point I found it's necessary, so that in case you come across such kind of a loading, you're able to resolve and of course now proceed from that point with your analysis. Now, if If I go back now to our 2D oriented bar element, and I start with this just oriented now in X direction. Sorry, the orientation is that if we are talking of a truss, if we are talking of a real truss with maybe those three members or three elements, so we say this is the global coordinate system, the overall coordinate system for the truss structure. So you use capital Y, capital X. Okay. So if I consider this member, if I'm considering now this member here, this member is like now I'm talking of this one. Okay. So it's oriented, the direction X in the local coordinate system corresponds to the global coordinate system capital X. And now we are saying for this node, at this point, the one we started with, the degree of freedom was 1. But now when I consider this member here, the second member, let me stick with the word element so that I don't confuse any one of you. So if we are talking of that element there, let's now extract it at this point. It will be oriented in that direction. So you see, if I was considering it individually, I just come and say this is the X direction, and then this is the vertical or the Y direction. This is the lower node, I, the higher node, J. Okay. Then I would go ahead and analyze, get the stiffness matrix, get the finite element equation formulation for the element, for the individual element. But now when I come to assembly, you find like these different elements are oriented in different coordinate systems. So to be able to assemble our stiffness matrix, we have to bring them to a common coordinate system, which we are calling it global coordinate system. Okay, it's like we are saying when they are oriented at different coordinate system, they are incompatible. But for us now to do the assembly, the stage, I believe stage 4 of our procedures for finite element analysis, it means we have to put them under the same coordinate system. And that's what we are calling the global coordinate system. So we need to do something we call transformation. We need to transform from local coordinate system to global coordinate system. And that's what we are doing today. Actually, that's basically all we are going to look at today, because once we are able to see how we can transform from local coordinate system to global coordinate system, because in a big structure, when we discretize, even if you're using softwares, different elements will be oriented in different coordinate system, but then the computer itself now will do the transformation and bring it to a standard or a common coordinate system, and then do the assembly or the margin, adding up of the matrices. So how do we do this? To transform from one coordinate system to global coordinate system, meaning it means we have to have a tool. And without even keeping it as a secret, I'll just say we need to have a transformation matrix. We need to get a matrix that we can use to transform from local coordinate system to global coordinate system. So if you look at this, we take an element. The second element that we have taken of our truss is oriented. The one I was sketching is oriented in this coordinate system. And if you look at it, you're seeing we have the node I, node J, similar to what we had in the coordinate system when we are just talking about horizontally aligned member. But now something interesting happened, is that, and at this stage, I think I can remove my video to stop blocking that. At this point now, you see the local coordinate system, small x and small y do not correspond to the global coordinate system. Global coordinate is the one that you are used to, vertical x, vertical y, horizontal x. And we are saying the notation you use capital letters to denote that is the global coordinate system. So each one of the elements oriented in different direction, finally we have to, or we are trying to transform them from this axis. You see there is this axis, the small y, the small x. We want to transform it to the global coordinate system. So we do this stepwise. What are we transforming? We want to transform quantities. We want to see what is the deformation. Like we want to see the deformation for our truss. Let's say you want to see the deformation. If I introduce another member here, mid-span deformation, deflection at this node. And you see we have different elements, this element, oriented in different direction. So we are saying like the quantity deformation U, we want to transform it to see overall for our truss structure, we want to see the transformation, or to transform the transformation, the deformation for this member in the global coordinate system, so that you can see what is the effect for the summation or the sum effect. All right. Now, we use some notation here. We are using prime, like an apostrophe up there, we call it prime. U, I prime, we are saying, is horizontal deformation in the local coordinate system. Now, because of this orientation, we are going to have a component in the y direction, which we are calling the VI prime, okay, in the local coordinate system. Because in the global coordinate system here, the deformation associated with y, we call it V, the vertical deformation. Horizontal deformation, we call it U. So for the global coordinate system, the quantities don't comprise of a prime. So we are using this prime, U prime, V prime, to denote quantities in the local coordinate system. And then when you move to the global coordinate system, it's not there. So consider a case here where this member, this element have stretched, or it have been displaced, it have moved, okay? So if it moves the way we are shown here, and for you to understand, we have applied a load to this truss, okay? We have applied a load to this truss here, okay? Then we'll have a deformed shape. Let's say this is the deformed shape here. The truss, our truss deforms something like that. This is hypothetical. It all depends with how the boundary conditions are. Let's assume something like that. So we are considering this deformed shape, and maybe now we are considering at this node where there is no support. If there is a support, of course, we know the node here doesn't move. But we assume a position or a point here, an arbitrary node where there is no support, such that we can have deformation both x and y. So if we enlarge this joint, we are saying the original element was like that. The deformed element will be something like that. So that our node here, if this was node, let's call node 1, the deformed one will be here. Okay. So if you look at it, we are saying there is both the vertical deformation V, and there is both horizontal deformation or displacement U. Okay. So this is what we are showing here. Like these elements have shifted to this location because of the applied load. So we are going to have a small vertical VI, and we also have this VI and UI. These are in the global coordinate system, but in the local coordinate system, we have this UI, this deformation UI. From this original position to this original position, we have that stretch or that displacement. Okay. So let me now show you, using this illustration here, what we are talking about: the local, global. Corresponding values, we are using small letters XY, global, capital XY. Coordinate, we said we use prime, but in the global, there is no prime. So in local coordinate system, we only have 1 degree of freedom per node. But in the global coordinate system, we have 2 degrees of freedom. Why 2 degrees of freedom? It's because I've already shown you in the global coordinate system, we may have vertical deformation and horizontal deformation. But because we know the member or an element can only carry axial loading, a global coordinate system, we can only have a stretch. We don't have any vertical stretching of the member because the load is applied axially. So the deformation is only along the axis or the horizontal axis of the member. So that's why we are saying for the local coordinate system, the degree of freedom is 1, just U. But for the global coordinate system, we have U and V. Okay, so we are saying for our individual member, if I go back, for our individual member, this member, the stretch is only either compression or tension. So it can only stretch or compress our individual member. But if we are considering globally, we are talking of a truss structure. The truss structure, we can have vertical deformation and also horizontal deformation. As I have shown in this case, we can have vertical displacement and horizontal displacement for a truss at the global scale. So you could put it at the back of your mind that when we are talking of global, we are talking of a structure itself, the truss structure. When we are talking of local, we are talking of an individual element. Okay, and that's what we are saying. For an individual element, because it carries axial load, there is no vertical displacement, of course, no vertical deformation. It can only stretch or compress. Okay, too much of that. So let's see how we do this transformation. I start with this bar element oriented arbitrary in that direction. So we are saying the group globally, we have this coordinate. Okay, like that. Of course, we can even have the negative direction. So we are saying this in itself, this is the global coordinate system. If it was a truss structure, then that is the axis, the coordinate system, capital X, capital I. And then what we want to do is that we want to resolve this component. Let's resolve component at this node, node I. So UI, and we are saying there is a component VI plane, but we are saying this VI plane does not contribute to the stretch of this bar element. What we are saying is that we have to resolve these quantities, resolution at the joint, the method that you did in the theory of structures, I believe, 1. We want to resolve quantities in this coordinate system small y to capital I, and we want to resolve these coordinate or quantities in the capital X direction to the global coordinate X. So what we do this, we employ geometry. Okay, we employ geometry. How do we do this? So we can drop, at this point, we drop, let me just show you very quickly something like this. So this way, or in this manner, I have dropped a line from this node perpendicular, like that. So perpendicular like that. Okay, in a similar manner. So I want to use similar triangles. So this perpendicular, perpendicular. So that I know if this is angle theta, the orientation of this member to the horizontal, then if this is theta, of course, this angle is 90 minus theta because it's right angle triangle. And then this being theta, it means this angle here is also equal to theta because this is 90, this is 90, this angle is 90 minus theta, it means this is theta. So in a similar manner, you can move very quickly and get for the other triangle on this side, this being 90, this angle itself here will be theta. And of course, now this will be theta. So I'm just using geometry. You learned that in your first year of geometry class. And now I can be able to use trigonometry to be able to relate between this axis and if this is y and this small y. I can use trigonometry to relate this small x axis to this capital X axis. How do I do this? I use trigonometry. So there are two quantities. I'm saying ui, I want to resolve it into this axis, So I can say, if I say use the cosine, cos theta, if I use this triangle, first one, cos theta is equals to, of course, adjacent over hypotenuse. So this will be your adjacent cos theta. If you see this is right angle triangle, so I'm using this triangle here. I'm using this triangle. I don't know whether I can get good marks. Yeah, marking here. I'm using this triangle here. Let me use it a thicker line, a little bit thicker. So I'm using this triangle here. Okay. So and this right angle. So when I say cos theta here, I'll be talking of adjacent is ui prime of a hypotenuse. This is equals to ui. Okay. So you can see I've been able to relate. In short, we can say u in the local coordinate system, ui is equals to ui in the global coordinate system cos theta. So you see, I can be able to transform using this trigonometry, the cosine. So in a similar manner, I can also resolve, because to resolve this component in this direction, of course, it have got a vertical component and a horizontal component. So the vertical component, I use a sine theta. So sine theta, now in this case now, because I want to resolve it around this, I use this triangle. So I see this right angle, I have this angle theta. So I can see sine theta is equals to opposite, which is ui like over hypotenuse. Now, this is now our global vertical, so vi. So in short, we are getting ui prime is equals to vi sine theta. That being the case, we say in total, if you add these two, we have resolved both in horizontal and vertical component. So you are saying ui prime in the local coordinate system is equals to ui in the global coordinate system cos theta plus vi sine theta. So we have been able to transform the local coordinate system displacement, horizontal displacement, to global coordinate system horizontal displacement using this resolution or the cosines and sines, right? Similarly, and this one you can do it at your free time. You can use this triangle and this triangle to resolve this vi plane in horizontal, in the vertical axis and the horizontal axis. You get the vertical and the horizontal component. And if you do that, you're going to get this as vi. So vi in the local coordinate system, vi in the local coordinate system, so you use plane, will give you a value equals to vi cos theta minus ui sin theta. Of course, minus here because we are talking of the negative x-axis. You are using this triangle and this triangle. So try that to see that you can be able to come up with this component. Now that being said, we are saying we've been able to obtain the ui and the vi, right? So you're saying if I rewrite them, let me just go back again. We are saying the transformation that we have done. Let me create some of this work. Let me remove this part. And what we are saying here is that this transformation, okay, let me see. This transformation here, ui and vi, okay, I can write it again here. Ui, we already did with ui prime is equals to ui cos theta plus vi sin theta. And then vi prime is equals to, now I can rearrange that. I start with the u. So this is negative ui sin theta plus vi cos theta. In matrix form, we can write this as ui in the local coordinate system, vi in the local coordinate system. You should be able to write well than me because I'm using a mouse. This is equals to, so you can see cos, sine, sine. So you have the ui, vi, ui, vi, ui, vi. So you're saying you can be able to put the ui global here, vi Remember, this is a displacement vector. We use braces. Here now we have cos. Let me just use C as cos, sine, and then this will be minus sine, cos. Okay. If you look at this keenly, you're going to see we've been able to transform from local coordinate system. Now I use bold this. U in the local coordinate system, or the displacement in the local coordinate system, to global coordinate system by using a transformation matrix. Okay? Because it's a matrix, so we've been able to remove the prime, because the prime represents this prime, this symbol here, prime represents the local coordinate system. So we've been able to transform the quantities, the displacement, the degrees of freedom, unknown quantities, or the deformation quantities, which is ui prime, vi prime, from local coordinate system to global coordinate system using a transformation matrix. And because this is just one node, the node I, yeah, these are quantities for node I, we've transformed to global coordinate system, node I. So we put what we call this symbol, this mark here, we call it at, I don't know whether you call it a tilde. Okay, it's like a wavy line on top here to say this just for one node. So it means when we come to this other node, we can do the same. Uj, Vj, it will be cos sine minus sine cos Uj, Vj. So this T, we're calling it T transformation matrix for a deriving node denoted by a tilde mark there. And in a similar manner here, I can use this space to say, or to write, or even to complete for Uj. Now U now here will represent both U and V. Uj in local coordinate system, now this is J, or node 2. Uj will be the same cos sine minus sine cos, because the behavior of this node is the same as the behavior in this node. Then this will be in the global coordinate system, will be Uj, Vj. Okay. So remember what I said about using just in a felt in a faint pen. So you know this one corresponds to Ui, Vi. This one corresponds to Uj, Vj. So what this tells you is that we can be able now to write an overall for this element, one element, for both nodes. We can be able to write the overall matrix Ui, Vi, Uj, Vj for both nodes. Okay. So to do this, what you do is you do what we call argumenting. I know you know what we say. Argumenting is like expanding. So if I wanted to introduce, let me create this space here. If I wanted to introduce the other node on this matrix, but it's not, we don't have element for it, we don't have members for it, or the quantity for it. So what I just say, I want to bring this here. I want to bring this one here to make it one matrix or one equation. So what I will do in this particular case, I just come here and then write Ui, Vi, Uj prime, Vj prime. So this will be now one combined matrix. And because I know this corresponds to Ui, Vi, let me remove also this part here for the time being. And then I know for this quantity there is Uj, Vj. So my matrix will expand like that. But I know Ui, Vi, the quantities for Uj, they are not interrelated. Node I and J are not interconnected. So these values will be 0, 0. In a similar manner, when I come to the point of Uj, Vj, or the secondary node here, the second node here, J, I know they are not interconnected with I, so there's no, they're not sharing the node. So the values here are 0, 0. And then I put here cos sine minus sine cos. Uj, Vj, which is this. this quantity. And then, of course, now I'll have the overall displacement vector for the global coordinate system, UI, VI, UJ, VJ. So this is what we call argumenting. We're introducing zeros so that we expand our matrix. That way we'll be able to add them together. So I believe so far, so good. Should be clear on your side. If there's any question, definitely you can drop your comment there. So this is what we are saying for the two nodes when you have joined them through argumenting. You can see UI prime, VI prime. And these are the quantity I'm saying. And be very careful. If you see me writing here UI, VI, these are not part of the matrix. So you can use a pencil when you are writing by hand. VJ, UJ, UI, VI, UJ, VJ. So these are the quantities. These are the quantities relating to second node. These are the quantities relating to first node. So as you can see, we are saying we can be able to transform quantities in local coordinate system to global coordinate system. So local coordinate system have got applying to global coordinate system using a transformation matrix. And now, because it's not just for one node, but it's for the whole element, our T now will be without a tilde here. Yeah, this tilde, we remove that. So you're saying we can transform from local coordinate system U, the deformation, to global coordinate system U using a transformation matrix. And all quantities in the local coordinate system, be it whether you're talking of force, whether you're talking of boundary condition, whatever quantity you are talking of in the local coordinate system, if it's force, small f, in the local coordinate system, this can be transformed using this transformation matrix to global coordinate system. Okay. So this is how we move from local coordinate system to global coordinate system using transformation matrix. So what you know is that, or what we look at now is in 2D space. Okay, in 2D space. And before I move out of this, this LM, L of course is cos theta, M is sin theta. This LM, we call them directional cosines. I know you remember this. Directional cosines. Okay, don't forget that. And of course, if you have this triangle here, let's assume it's a triangle. This is a IJ. Of course, now you know directional cosine cos theta is adjacent over hypotenuse. Sin theta is opposite over hypotenuse. So once we are able to transform or to do the transformation, we can move with confidence now to obtain this. What I was saying. In the local coordinate system, you can be able to transform the deformation. You see what I'm saying in type, in books, and when you print, you can print in bold. Now, when you print in bold, you don't have to put the braces or the bracket. But when you are writing by hand, then it means you have to put the, if it's a rectangular matrix, you have to put square bracket. If it's just a vector, it could be a column vector or a row vector, then you have to put the braces. So you can see, this is for one node, the transformation matrix for one node. It is T, the matrix T with a tilde here, and this one with a tilde here. So that you can see the way they are arranged when you have now for the overall, for both nodes. So the nodal forces or any other quantity we said it can be transformed. But this is nodal for the node, for one node. Okay. So when you want to obtain the stiffness matrix, this one we move very quickly because we already derived this. So the stiffness matrix for a bar element, we said K, elemental stiffness matrix is equal to EA over L, 1 minus 1 minus 1, 1. Okay. And then when you talk of the finite element equation or the equilibrium equation for an element, elemental, you just need to introduce the displacement vector and the force vector. So you see now for the element, local coordinate system, we have this line to designate that we are the local coordinate system. So we need now to see how we can create the stiffness matrix for the global coordinate system. How do we transform this? So augmenting this equation. Why are we augmenting? We want to have the coordinate, the V component. You know, in the local coordinate system, when we started off, we never had V because it was oriented, that this was the orientation of our member. So we are only concerned with the horizontal displacement. But when it's oriented like this, we are saying there is a component, a vertical component, even though at local coordinate system, that vertical component is kind of virtual. It doesn't contribute to the stretch of this member. But globally, the vertical component is important because our truss structure will have both vertical displacement and horizontal displacement. Okay, so we want to introduce, we are augmenting to introduce the vertical component. So doing so, what we are saying is that just introduce, you know, this was related to UI plane, UJ plane. So you want to introduce UI plane, VI plane, then UJ plane, VJ. And because we do not have component for VI plane, so all that is associated with VI plane and VJ plane, all those quantities are 0. We know for the local coordinate system, there will be 0. They do not contribute to a stretch. So even in the matrix is 0. But for the global, we know there will be quantities. Yeah, our truss structure will deform vertically and horizontally. So far, I believe everything should be all right. I can see in the chat area, there's no query so far. I know, of course, maybe you are taking time to digest this, but it's quite simple. It's quite simple if you follow it step by step and also do the workings. So looking at this, let's move, because our target is now to move to get the stiffness matrix for the global coordinate system. So you see, we have this at local coordinate system. Of course, F is equals to KU. So if you use the transformation, we say any quantity in local coordinate system can be transformed into the global coordinate system by use of transformation matrix. Like we know, this U, of course, we said U in the local coordinate system, U prime is equals to transformation matrix times U in the global. F in the local coordinate system, we said, can be transformed to by multiplying with the transformation matrix, then that's global. So this is just what we have done. This is this, and this U is this. So if you look at this carefully, we are pre-multiplying transformation matrix with F. The order is very important. Otherwise, you might interchange and then you find like they are not compatible. I remember I told you from lecture 1 that you should kind of revisit matrices because you do a lot of matrix operations here. And that's why you find like sometimes this course in some books you heard it being referred to as matrix analysis of structures. Now, remember our form of finite element equation is F is equals to K U. Okay, so if you look at this, we have T here. We want to remove this T here. If you look at this transformation matrix, if I go slightly backwards to this slide, we have this is our transformation matrix T. If you look at it, we only have quantities in the major axis. We have quantities which are similar, and then we have, it can be mirrored. This quantity mirrored here, this quantity mirrored, of course, with this negative. So what we are saying is that, or if you look at it, there is a unique property that this matrix have. And we say this matrix is orthogonal. T is orthogonal. Matrix T is orthogonal. What we say by this is that T transpose is equals to T inverse. And we are talking of for this node. If you take this, just start with this small one. T transpose is equals to T inverse. And for an orthogonal matrix, one characteristic of, or one feature of it is that if you multiply T with its inverse, T times T T transpose times inverse, you are going to obtain T transpose times T, you are going to get an identity matrix. You can try that. Okay, you get an identity matrix. Remember we said that T transpose for this orthogonal matrix, when you look at it, is the same as T inverse. Of course, transpose is like you exchange rows and columns. So if we put this, if we exchange this, so T transpose, I didn't want to revisit this matrix with you, but just as a reminder, T transpose, this will be L, this M comes here, minus M, and then M becomes here L. So you can try also getting it inverse, the inverse of this matrix. You're going to find like they are the same. And if you multiply like that, you're going to get that identity matrix. Or T inverse times T is equals to identity matrix. Identities in matrices, an identity matrix in matrix is kind of one, because we are saying is a matrix where only the main diagonal have got quantities, which is one, but anything else is zero. So an identity matrix is the same as saying value one. All right. So we move now to this part. So we are saying, if you look at this equation, so it means, because we already know, we know at the back of our mind that the form of our stiffness matrix, of our finite element equation is like this. If we can be able to eliminate this T from this side, then whatever you have on this side, you have U, whatever that will be formed here will be equals to the K in the global coordinate system. So what we do is by multiply with the transpose, because we know that T times T transpose is an identity matrix. So it's kind of one. Then we multiply here with T transpose. And this is what we are doing in this next slide here. We pre-multiply with T transpose. If we pre-multiply with T transpose, of course, identity matrix are just like one. So you're having this as our equation, F is equals to all this. And as you can see, we have this component all the way to this part. So this is like K in the global coordinate system, because you already have the U in the global coordinate system and F in the global coordinate system. Okay. So, and in short, we are saying K, this is the K in the global coordinate system. T transpose K in the local coordinate system times T. And now this is the elemental stiffness matrix K in global coordinate system, how we transform from local to global. After that, if you have been able to get the stiffness matrix, because we at the global coordinate system, now you can go ahead, because once you have the stiffness matrix, we follow the order. Once we do the transformation, we follow the order of the 7 steps or the 8 steps of the finite element analysis. And we can do this now with an example. So if you do that, this you can do in your own work. If you want this out, we have the transformation matrix T, which was cos, sine, minus sine, cos. And maybe, I don't know how you want to do it, but if you look at this, transformation matrix is very easy to recall, because you just need to remember this part. Okay, so you can see this part is similar to this part. So it's like this one is copied here, this one is copied here, and then everything else is 0. Okay, so this is the transformation matrix. Now for our stiffness matrix, this you need to do the pre-multiplication. T transpose times K in the local coordinate system times T. Of course, all these quantities, you have them. Okay, so you're going to get K, you have it. K is this. Of course, you have to pre-multiply to multiply using this argumented. From the local coordinate system, it was this in a condensed manner, but we argumented so that we can introduce the component for VI apply. Okay, so this is the K. This is the K in the local coordinate system. So this is a small K here. This is a K prime here, not a small K. This is a K prime here. Then there's the matrix T, we have it. Of course, we say del M minus ML, then you have 0, 0, 0, 0, then 0, 0, 0, 0, LM minus ML. You see, you can remember it quite easily. So with that in mind, so you just need to come here now, pre-multiply with that, and you're going to get this quantity. But again, it's also very easy to recall this because this part and this part is the same. Okay, and then you just know that this is square. The first quantity is L squared. The opposite in the main diagonal, L squared, M squared, then LM, LM. Same case here. So it's like you are copying this one here. Then the other are the same, only that the signs are negative. So this one, you copy it here, but it will have negative sign. And you copy it here, negative sign. But I'm not calling you to recall this, calling you to work out this. Get T transpose, multiply with K local coordinate system times T to see whether you can be able to obtain this equation. Because this question is very important. This is the stiffness matrix at the global coordinate system. All right. Then from there, we can be able to obtain the elemental stresses. One thing that you have to notice that we stated categorically that the elemental stresses, the VI plane does not contribute to a stretch. So because basically what we're talking of is the stress in this member, stress of course is equal to force over area. And the stress in this member, we just need the quantity that contributes to a stretch, whether be it negative or positive. Of course, negative stretch is compression, depending on the type of the axial that you have applied, whether it's compression or tension. So we need to disregard the quantity VI and VJ in the local coordinate system. So what we need to do is that we know, of course, this displacement, what we call the strain displacement matrix B, and if we are to pre-multiply UI, VI. So what we do here is that if you move to slide, I don't know whether I'm calling it 42. What is slide number 42? In your slides, this is slide. Let me see. In your note, it should be where we derived this. It should be this slide. We did this last week. Okay, I didn't want this. I wanted this. I wanted to show you this stress where we derive the stress. Strain displacement matrix. Oh, we did it by heart. It was in this slide. I did 48. But even without looking at that so much, what I know is that you can recall we derived the strain displacement matrix and also the stresses. So what we are doing is we are just taking the rows and the columns. If you come to the equation, if you come to the equation on slide number, let me confirm that. Count the equation on slide number, transformation matrix. So if you come and take the transformation matrix, this transformation matrix. So we are saying what you need to remove, what you are ignoring is rows and columns associated with VI. You know, this is UI plane, VI plane, UJ plane, Vj prime. So for the stress, we are ignoring these rows, columns and rows that are associated with Vi prime and Vj prime, because they do not contribute to the stretch of this member. So that now our transformation matrix, we are only going to have these quantities, the one that are not cancelled. Ui prime, Uj prime. This is what is happening in this slide here. Okay, this is what is happening here. E multiplied by E, then the displacement matrix like that, minus 1 over L, 1 over L. You can visit the last week's lecture to see how we derive this. Then LM00 like that. So that is, we are in condensed format. This is how we are rearranging. This is the equation for getting the stress in this member. Of course, you just need to disregard the Vi prime and Vj prime. Okay. Okay, so much of the derivation. Let's look at one example. We see the application so that this concept that we have looked at can condense, or they can sink into your mind. Okay. So if you look at this, we have a two-member truss. We have a two-member truss, and then you're given the quantities. They are identical. These bars are identical. They have the same material property E, and the cross-section A, and the length L. Then you're told to find the displacement at node 2 and the stress in each bar. Of course, to get the displacement at each node, you need to get first we need to get the stiffness matrix for each of them in the rock coordinate system. Then we transform to global coordinate system. We get the overall stiffness matrix. Then we get the overall finite element equation. Then we can be able to solve for the unknowns. Of course, you know, for stiffness matrix for a bar element is equals to EA of IL. This should be at your fingertips. 1 minus 1 minus 1, 1. But these are the local coordinate system. So we put apply there. So that is why we are saying K for the each of these is equals to, because they have the same material property and geometry, 1 minus 1 minus 1, 1. But you see, now we cannot assemble them because they are oriented in different coordinate systems. So we need to get K1 in the global coordinate system and K2 in global coordinate system through transformation. And of course, we know, did we obtain this? We know K is equals to EA over L, or instead of even writing this one here, you just need to revisit this. K is equals to EA over L, this. Okay, so what do we need to get? We need to obtain the directional cosines. So the angle of orientation is very important for different elements. So EA over L for K1, E1, A1, L1 over that, then this quantity. So what do we need to do to get the direction cosines? We need to get this angle. And to get the angles, we get the orientation. And this is how we get this is how we read angles. The horizontal x-axis counterclockwise, that is positive. That's how we read them. So if we are talking about this element 1, and then we read from node I to J, where I is the lower node. I is less than J. So we do not read from node 3 to 2. We read from node 2, 3. So for element 1, we say 1, 2. This is the horizontal. This is the angle we are talking about. Positive 45. So for element 1, theta is equals to 45. For element 2, theta is this angle. From positive x-axis counterclockwise. Right? So this is, if this is 45, then this is 45 also. Then this is 90, so this will be 135 degrees. So with those angles, then you can go ahead and get the directional cosines. Okay. So using that formula, you get EA of L. So of course, for element 1, when theta is 45, you can use, for these angles, 45 and 60 and 30, you can utilize special triangles to simplify your working. you can also start punching the calculator, but you do it so much, you know, and you should be smart. As engineers, you should be smart. Where you find something that is unique, and you know that we have a short way or a short form of executing that, then you should go ahead and utilize a truss property. So of course, for special triangle, if you I don't know whether you still recall that we said this was in maybe in high school or in a graduate first year. So if this is 45, and then this is 45, this is 1, this is 1, this is 1, is 1, this is 2, because it should be 1 squared, 1 squared, squared plus 1 squared, 2, is it? So that you get, now did we use, yeah, so that you can get cos theta, cos 45 is equals to adjacent over hypotenuse. And then you can rationalize this. If you rationalize by multiplying by root 2, so you get root 2 over 2. This is what we are obtaining. You can do the same for sine. And you do that. Of course, now you remember our transformation matrix K had, this was L squared, M squared, LM, LM. So this one you just copy it here to be negative. Then this one is the same here. This would be the same here, but negative. So you can see like we are multiplying with either of them. So you can say either of these will have this one squared, so that you'll have this as 2 over 4 or half. It means we can take 1 out here, 2. This way we are having this 2 here, and then everything else remains as 1 with the signs observed. So work that out, then you see you can be able to obtain that. It's as simple as ABC. So this is just reminding you of how we obtained the global stiffness matrix. This was a formula, but remember we have already derived. So you don't have to go from first principle to derive this part, because you already derived what is K global, which is equals to EA of L, then L squared, LM, and so on and so forth. So you do this for K1. So the difference will be for different elements, they'll be oriented in different direction. So the angles will be varying. So the direction cosines will be different or be varying. Okay. So you do that for element 2. You do the same for element 2. Beta is 135. You get what is L, what is M. So basically now you get K2 is as shown here. You see, we are utilizing this global coordinate system here because we have already now moved to the global. This is in the local side, this is in the global side. So U2, V2, U3, V3. This one had U1, V1, U2, V2. Now you can assemble. You see, they are in the global coordinate system. You can assemble. They are in the same coordinate system. You can get the assembly. And the assembly is just the same way we did. Reach that, you get U1, V1, U2, V2, U3, V3. You use the compatibility condition to be able to get the quantities for U1, U1, get that. Then you obtain this overall stiffness matrix. So here, this is the K, the overall stiffness matrix for the whole structure. So this is the capital K. Then we have the displacement vector in the global coordinate system. And then we have the force vector in the global coordinate system. And you see now the force vector will have both. If it's at node 1, we'll have the X component, the Y component. Of course, we can have vertical value and horizontal value of reaction here. Okay. And that's as simple as that. Once you have done this, we have done the transformation. It is very simple now. From here is the stages, the step that you have followed. To go ahead to solve for the unknowns, you invoke the boundary condition. You see, this is pinned, this is pinned. So there will be no vertical deformation here. There's no vertical translation or deformation. No vertical degree is 0. So U3, V3, U1, V1 is equals to 0. So this is 0, this is 0, this is 0, this is 0. Okay. U2, V2, of course, there will be deformation here. Then P2, this is F, 2 in the y direction. This is F2 in the x direction. So F2x is equals to P1, F2y is equals to P2. So we say to solve this, to simplify this, you first remove the rows associated and the columns associated with quantities with the 0 displacement. So U3, V3, U1, V1, you remove this row. So what you are left with is this part. This, and this. Okay, and this is now very simplified. You can go ahead and get, you have invoked the boundary condition, so you can go ahead and solve. This is our simplified equation, condensed equation, EA2 of 2002 U2, and now this is a very simple simultaneous equation solving. You to get what is U2. U2 is equals to P1L over EA, V2 is equals to P2L over EA. Now, for the stresses that are required to be computed, I'm moving quickly because now this is a simple what we have been doing in the previous workings. The stress in 1, of course, we derive this equation. It's equals to E of I like that. You can go back to equation 7 that we just derived. So it will be just a matter of, once you have determined what is U2, V2, just a matter of substituting them to get what the stress is in. Stress in number 1, stress in number 2. Okay, that can be seen. And it's as simple as that. So what was so important in this lecture today was about how do we transform. First is derivation of transformation matrix, so that we can be now working with quantities in global coordinate system. It should click at the back of your mind that we cannot assemble stiffness matrices for different elements which are oriented in different coordinate system. We have to bring them to the same coordinate system. And we do this by using or employing transformation matrix. And we have seen how to derive that transformation matrix. And we say, I know we have transformed maybe only the deformation U. We said any quantity in local coordinate system can be transformed into global coordinate system utilizing the transformation matrix. And this is now the test in this example. So this example is nothing complicated, nothing much. Only what is happening is that if you look at this, like support 3 and support 2 and support 1, all of them are oriented in different coordinate systems because support 3 is Aurora support. But if you look at it, this is its horizontal direction and this is its vertical direction. So the boundary condition are oriented, they are in different coordinate system. Of course, this one and this one, they're in the same coordinate system. And the overall global coordinate system is the usual y and x that you know, horizontal and vertical. It's indicated here, this x and this y. Okay. So with that, so only what we need to do. The other time we were transforming, displacement. Let's see when now it's boundary condition, what will be transformed. So if you look at this, we are given, of course, this is the given information. You are to determine the displacement and the reactions. Displacement at either of these nodes. So you have to look at the boundaries condition so that you determine which ones are unknown. There are those that you can already determine them outright. If you look at this pinned support, there's no vertical, no horizontal displacement. So U1 V1 is equals to 0. The other support 2, there is Aurora. It can move in the horizontal direction. So there can be a displacement in the horizontal direction, but not in the vertical direction. So V2 is equal to 0, but U2 there is a vary. Now this is the one that will be interesting. In the global coordinate system, U2, U3 and V3, they are different from U3 prime and the V3 prime. So it's kind of, we need to determine these quantities, U3 prime, the coordinate system, and then we transform that into the global coordinate system. Let's see. So there is something that we're going to jump on. But in an exam setup, of course, you can't do that. You have to solve it. What we are saying is that to get the global stiffness matrix, right? You just need to come here and obtain what is the orientation. So like element 1, this is element 1, already it's given for you. So element 1, what is this angle? From the positive x direction, this is 90. So for element 1, theta is equals to 90. So you can be able to get what is K1 global, EA over L. And I don't know, look, you can look back here. You can go back to see the information given. You are told element 1 and 2, A is equals to this value. Element 3, A is different. So be cautious of that. Again, L is 1. So if you have this value 1 and these angles, you should be able to determine what is L2, what is L3. Then you are given for all of them, the material property is the same. So E is equals to 210 gigapascals. So note that when you are now substituting EA over L for K1, 1, L is equals to 1, E is given, and A, of course, is given. So you get K1, K2, K3. Once you determine, like now K2 here, the horizontal direction is that. But we are talking of node 2, 3. So theta 2 for element 2 is equals to 0. Theta 2 is equals to 0. So you can go ahead and get the direction cosines and get what is K2. For K3, element 3, we move from the row node I, J, 1, 3. So theta from the horizontal axis is equals to 45. So if this node was 1 and this was 3, we could have moved horizontal x direction. We move like that because we move from the lower node 1 to higher node 3. So this, the whole of this angle. Of course, if you move in the shorter direction, if you want to move like this, then the angle will be negative. And if you do the direction cosines when it's negative, of course, you're going to get the same values. Okay, so that should stick into your mind that angles are measured from horizontal x-axis. For the nodes, we move from lower node I to higher node J. Once you do that, you get the overall stiffness matrix. You should be able to get this. This is the global stiffness matrix. This is the global stiffness matrix for the overall structure. So this is your K global. Of course, this means it's symmetrical. So we are saying whatever is on this edge can be mirrored along the main diagonal to get here. And this is typical of all stiffness matrices. If you have observed all the stiffness matrices that we have determined, that's one feature or characteristic of stiffness matrix. It's symmetrical. Okay. Then you have introduced the displacement vector and force vector to obtain what we call the equilibrium equation or the finite element equation. So from this point now, it's just to go straight ahead and invoke the boundary condition so that you can start solving for the unknowns. We are solving for the reactions and the displacement. Now, what do we know? We know U1, V1 is equals to 0. So this is equals to 0. This is equals to 0. We know V2 is equals to 0. So V2 is equals to 0. What other information do we have? Because if we derive this, we'll have how many equations? 1, 2, 3. We'll have 3 unknowns. But we are given a condition here. We see this is roller support. So U climb 3 is not equals to 0. Okay. But we know V climb 3 is equals to 0 because of this roller. There's no movement upward, but it can move to and from. Okay. So V climb is equals to 0. So we can neutralize this. We can resolve this boundary condition, the displacement that we know, to the global coordinate system. We can utilize that condition to be able to simplify further our equation and solve the unknown. Okay. So this one you can refer to our initial equation because we are talking of resolving just one quantity at a node. You remember how I started the derivation? We started the derivation by deriving at a node. And what we noticed is that from our, I believe we done it here. Why I'm not going backward is because I know I was working by hand. I don't know whether you are making the notes. We are working it out here when we started by deriving for one quantity. And then we said, like here, I remember we talked of UI being equals to UI VI. So this direction cosines, we obtained the UI in the local coordinate system. Or let me stick with the VI because we are going to resolve. We are going to resolve for. I delete this. We are going to resolve for V. So we found that VI. Let me bring this sketch here. So we found that VI. This is VI was equals to minus UI cos theta. Let me just say cos is L. So cos theta plus VI sine theta. Okay. Or you write it in matrix form, which was no UI, this is sine. And then this is cos. You can revisit that. So this was in matrix form, this was minus M L or minus C minus SC, then UI VI. And so, in short, what we are saying is that for this problem now, because we already know what is V3, we already given here this V3 prime is equals to 0. Okay. So we can be able to transform the relation V3 prime. So I now is 3. So we say V3 prime is the same as minus M L U3 V3. Okay. U3 V3. So this one now becomes very simple because you just need to get the direction cosine M L for element 3 because we are talking of this 3. And the angle is 45. So you need to get what is cos 45, sine 45, cos 45. So this one will become shown in this slide now. So this is, this is what I was calling UI VI equals to LM minus ML UI VI. So for V3, now we get minus ML. So cos 45, so minus this is U3 V3. You can simplify this. And we are saying V3, right? This V3 prime is equals to 0. So we equate this is equals to 0. So if you solve this, if we try to solve this, you are going to get like U3 is equals to V3. And this is what we call a multi-point constraint. There are many points, this one, this one, this one. Constraint different, many points. Then U3 equals V3. So if you go the same case, you can do the same for the reaction. You know, we are going to have the reaction here. The F in the global coordinate system, node 3 in the X direction, and the vertical reaction, F 3Y. Okay. In a similar manner, we know F3X. We know F3X this direction. Because of this aurora, there's no reaction in this direction, is it? Of course, if there's no rod, there's no reaction. It's not restrained. So we are saying F3x in the local coordinate system is equal to 0. If you utilize the same relation, we are saying F3x in the local coordinate system is equal to this quantity. Then here you have F3x in the global coordinate system, F3y in the global coordinate system being equals to 0. And with that, we are going to get like F3x in the global coordinate system is equals to minus F3y. So you are simplifying the values of unknown. You are reducing the values of unknown in your equation. So we had already said from inspection, U1 is 0, V1 is 0, F1 is a value there is a reaction. F2, F2x is 0 because of this roller. Then F3x, we are saying is the same as F3y. So it's like we are saying F3x and F3y. So this is the same as minus F3x. Okay. Again, if you look at what we have derived from V, we are saying U3 is equals to V3. Of course, we say the V2 is equals to 0. U3, so this V3 is equals to U3. So you see, you have reduced the number of unknowns. You only have U3 and U2 as unknowns. So you have simple equations in two unknowns. Okay, and then of course this one which are 0, you can just go ahead and remove those rows and columns associated with that. You are left with just those associated with U2 and U3 to solve the equation. So once you do that, it's not just now a matter of going ahead and solving it the same way we have been solving for the other. So you apply the row boundary condition, you delete, of course, those rows and columns that you are associated with 0 displacement. So you have a very simplified matrix. So what we are doing is that we are invoking boundary condition because we are solving boundary value problem. We say without boundary values defined, we have not clearly defined our boundary value problem. Okay. So now U3, you see from this equation, we had U3 and V3, but you said V3 is equals to U3. Again, we have F3x, F3y, but you see the F3y is negative F3x. So you can see, go ahead and see it's simplified. You only have U2, U3 as unknowns, F3x as unknown. So you go ahead, solve that. This simple matrix operation. So you get F3x is this value. You get, because now you start substituting, it's just a matter of solving. You're able to obtain what is U2, what is U3, and then you can be able to obtain all the other quantities, what is F1, F1y, and so on and so forth. Okay. So work that out. It's as simple as that. So the objective of today's lecture was to derive elemental stiffness matrix for a bi-element oriented in 2D space, and we see how we can use that transformation matrix to transform from local coordinate system to global coordinate system to enable us have matrix for different elements oriented in the same coordinate system to assemble, to enable us to do the assembly. After the assembly, now we proceed with the standard procedures of solving for finite element level. And that's it from my end. Of course, you can extend this to 3D, but the procedures will be the same, only that now the size of your matrix will increase because we'll be having F1x, F1y, F2x, F2y, no, F1x, F1y, F1z. Okay, if you have the z direction. So you'll have larger matrices. So for hard calculation, we can stick with 2D space, but of course, you know, when you go to using a software, now it's a software that's calculating, because you may be dealing with this kind of a truss bridge. Yes, a truss bridge. Yeah, you just need to model it. Okay, maybe a truss bridge like that. Let's say it have got that kind of a configuration. Okay. And then you just need to define this. You just need to define, and then it's braced. You just need to define this model, and then material property. You see now this one will have the vertical y direction, the horizontal x direction, and of course the depth z direction. So our matrix will be larger, but when you define, and you see now for each of the elements, like now here we have, if you go back to this, before we reduced our matrix, it was a 1, 2, 3, 4, 5, 6, 6 by 6 matrix. 6 by 6, defining the number of degree of freedom. So you're saying there are 2 degrees of freedom here times 3 support. So those are 6 degrees of freedom. So you can imagine for this kind of a structure, for all these members, how many degrees of freedom and what will be the size of a matrix. Okay. So when we go for a 3D, each node have got 3 degrees of freedom times the number of nodes. So that will be the size of the matrix. And that's why we need now the computational power of computers to help us now in solving these matrices. But we have understood the basic principle of operation of this matrix. It's just addition and reduction using the node boundary condition. So if you don't define adequate boundary condition, or if you over-constrain your structure, you'll be try to run your analysis, let's say like in Abacus, then it throws an error. Maybe it tells too many constraints, maybe, you know, so we are defining an issue, I mean, not an issue, but a boundary value problem, and the boundary condition have to be well defined for our analysis to be tenable. Okay, I'd like to edit at that because we have already went past our time. And when I look at the chat section, I can see there is no question. Nobody have raised any question, meaning either you have understood everything or you're still digesting it. But I give you time to look at this. One thing that I will advise you is that don't just look at these solved problems like the way you are looking at them. Work them out. Because as you work them out, that's how these concepts are going to be instilled and get ingrained into your memory. So that's it for today. Next week, we move to the beam element. If you have any question now or later on, you can still drop it there. If there's no question, I just leave you at that. All right. I believe last time, did I leave any small exercise? If there's a small exercise I left, we should have that. No, I did not leave an exercise because I had already given you the typical solution for this. All right, that's it for today. Thank you for your attendance and participation. In any case, if you have any question later on, you can ask it and then you'll address it later. So if no question, then I'll just edit that. We say we meet next week. Bye-bye.